The last page of your handout has 3 limits that we might try to explore. If we try to explore them using substitution, we would have no luck, because in each case we'd end up with a problem where we end up dividing by 0, which is undefined. So I want to introduce 3 algebraic techniques that you might consider if you're faced with a limit that is not well behaved. So these are examples of not well behaved functions. And I'll show you what you could do. So you'll see there I wrote on the paper 3 possibilities. One of them is to factor, and then possibly, if you have matching factors in the numerator and denominator, to cancel. This is what happened with our instantaneous speed problem from a couple of nights ago. So watch what happens here, because I really want you to practice the notation. The algebra is important. It's not like the biggest deal. The reason this is super important to me is because I want you to be practicing using limit notation. So here we go. I'm going to show you what I would write. I would say the limit as x approaches -1 of this rational function is equal to the limit as x approaches -1 of, and I would factor, I'd factor numerator and denominator, except the denominator doesn't factor. You will find that your success in calculus, well, the amount of fun that you have in calculus will depend on how well you remember how to factor. But I'll admit that factoring here with a leading coefficient that is greater than 1 comes up very infrequently. I would be surprised if it ever showed up on the AP test. They do a really good job of trying to make the algebra not a focus, so they can make a calculus a focus. But let's just come over here, and I'm going to factor 2x squared minus x minus 3. Spoiler alert, if this is going to work at all, I'm going to have a factor of x plus 1, so that I'm going to cancel with the denominator. So when I factor by guess and check, which is not the only way to factor, but it's the way I'm going to try here, because I already have this sort of a premonition that x plus 1 is going to be a factor. If x plus 1 is a factor, then this must be 2x. This is going to have to be the number 3, and it's going to have to be subtraction. So then I would confirm x times 2x makes 2x squared minus 3x plus 2x minus 3. And I've confirmed for myself that that does multiply back out. So this is a correct factorization, x plus 1, 2x minus 3. So since we don't actually care what exactly happens to y at the place where x equals -1, we really only care about what happens as we approach -1 from the left and the right. Canceling out this common factor does not affect the limit value, even though it will very well affect the function value. This is legal to do when we're talking about a limit. So I'm going to say that now this is the limit as x approaches -1 of, my x plus 1s have canceled, and I have 2x minus 3. So now that I've arrived at an expression that is extremely well behaved, 2x minus 3 is just linear. There's no holes or jumps or gaps or divide by zeros in it. So now this is going to be equal to, I don't need to write the limit anymore because I'm going to make my substitution. 2 times -1 minus 3. So my limit is -5. Final answer. So let's introduce a second technique. Right now, if I were to try substitution, I might let x equals 16, and that's going to give me a 0 in the denominator. So I cannot evaluate this limit by substitution. Another technique we might try, if you have a radical expression in the numerator, it's called rationalizing the numerator. You're probably familiar with rationalizing the denominator, because we have sort of a mathematical understanding that we don't leave radicals in the denominator if the final form of our answer is especially important to us, if we're going to compare it to other people's work. But you can use the same process to rationalize the numerator. And even though it will give you a radical in the denominator, it'll get us away from our divide by zero problem. We'll be able to make a substitution in, and then we won't have a radical in the denominator anymore. So let me show you what that looks like. If the limit as x approaches 16 of square root of x minus 4 over x minus 16, that's going to equal the limit as x goes to 16 of, to rationalize, you're probably used to rationalizing the denominator. It doesn't matter if it's the numerator or the denominator you're trying to rationalize. If I want no more radicals up there, I have to multiply that numerator by something that's going to make the radical go away. So if I want to cancel out that square root of x, what I'd really like to do is square it. But it's not legal to just square the top and the bottom of a fraction. So my other option, I hope you've heard the word conjugate. We're looking for the not the complex conjugate. That's probably the context in which you heard the word conjugate. We're looking for the conjugate of that numerator. So the binomial that has the opposite sign in the middle. So I'm going to multiply the fraction I have, the rational function I have, square root of x minus 4 and x minus 16. I'm going to multiply the top and the bottom by the conjugate of the numerator, because it's the numerator I'm trying to rationalize. The conjugate is square root of x plus 4. Now, to be fair, I have to multiply the denominator by square root of x plus 4. Here's the good news. I'm going to end up with no radical in my numerator. And if you were worried about doing the 4 multiplications it would take to multiply the 2 denominators together, I don't want you to do it. If this is going to be a successful algebraic operation to get me to find the limit, which means getting rid of my 0 in the denominator problem, then I'm not going to want to multiply those together. I'm going to actually want to leave them as a multiplication problem, like as an expression. Do not do the 4 multiplications, just leave that factored. Watch what happens in the numerator. I'm going to make my 4 multiplications. Square root of x times square root of x is x. Square root of x times 4 is positive 4 square root of x minus 4 square root of x. That was the whole point of picking the conjugate. It makes the middle terms cancel out. And then I have this negative 4 times a positive 4 to make minus 16. Well, I'm glad I left that denominator factor, because now I notice that this x minus 16 in the numerator will cancel the x minus 16 in the denominator. Do not forget that when you make a cancellation like that, you leave behind a 1. So this is going to be the limit as x goes to 16 of 1 over square root of x plus 4. Don't panic about having a radical in your denominator, because the whole point here, I'm just going to move up to my next line. Once substituting 16 in does not give me a division by 0 problem, it's legal to substitute it in. So this is going to be 1 over the square root of 16 plus 4, which makes 1 over 4 plus 4 to make 1 over 8. Final answer. I want to make sure you notice where I stopped using the limit notation. This is the last place I had the limit notation. Once I get here and I look at this expression, I ask myself, wow, okay, this is way less complicated than the step before. So I'm going to stop and check. Could I substitute 16 in for x without giving a divide by 0 problem? Once I notice I can, I'm going to make that substitution. I'm no longer finding a limit. I have an exact value. In this case, the function we're trying to find the limit of is what's known as a complex fraction. It's a fraction with fractions in it. Or a rational function, so a function that's the ratio of 2 functions, 2 smaller functions, and one of those or both, but in this case 1 contains a fraction. So I thought maybe it would be helpful if I just rewrote that so it looks more like fraction. In the case where you have a complex fraction that you're trying to find the limit of, algebraically, it is usually very effective to find a common denominator. The same way you would simplify a complex fraction. Try to make one fraction in the numerator so that you're dividing a fraction by a fraction, and you can change to multiplication by the reciprocal. So I didn't do any new math. I just wrote it out because I see now the way that's printed on your paper, the fractions don't really look very much like fractions. So I just changed this notation to be a horizontal fraction bar. Okay, so now that I have this limit problem, I have to just always check, because sometimes you really can just substitute in this x value. But if I try to substitute in x equals 0, I'm going to have a divide by 0 problem. So I need to think of something smart. My suggestion to you, you're going to take the limit as x goes to 0, and I want to just focus on the numerator of this fraction. What I really want is to turn that into one fraction, but right now it's two separate fractions being subtracted. Well, the way we subtract two fractions is to find a common denominator, so that's your first step. If I need a common denominator for x plus 4, and 4, it's a little bit ugly. I'm going to have to end up multiplying the second fraction by x plus 4. Let me make it a different color. X plus 4 over x plus 4. I'm going to have to multiply the first fraction by 4 over 4. Notice I'm not going to mess with anything about that x for right now. He's not the problem because he's not a fraction. The big problem here right now is that I have a fraction in my fraction. So now here's my subtraction in the numerator. Don't bother multiplying out that denominator. This is going to be 4 times x plus 4. My numerator is going to be 4 times 1 to make 4, minus. I'm going to have the same denominator now. That's what I was hoping for. And here I'm going to multiply the numerators. 1 times x plus 4 makes x plus 4. And my denominator is x. So that doesn't look complicated. That doesn't look less complicated. That looks more complicated. But now that I have a common denominator in the numerator, I'm going to simplify the numerator. If I can write one fraction in the numerator, I'm going to be really close to evaluating this limit. So this is the same as the limit as x goes to 0. The denominator is x. In my numerator, I have a common denominator of 4 times x plus 4. And the question is, what do I get when I combine those numerators? I have a 4, take away x, take away 4. So don't forget to distribute that subtraction. You're going to hear a lot more from me about this, but not distributing that subtraction in a scenario like this is the #1 most common algebra error from calculus students. So I think this 4 and this minus 4 cancel out, and I'm going to end up with negative x up here. So it's 4 minus x minus 4. 4's cancel out, and I have a negative x. I'm going to come up here now. I still have a substitution problem. If I try to substitute 0 in, I still have x in a denominator. So I have to keep my limit notation. But recall that if I want to divide a fraction by something, I can multiply by the reciprocal instead. So I'm going to think of this as negative x over 4 times x plus 4. And instead of dividing by x, I'm going to multiply by 1 over x. I'm going to notice that this x and this x will cancel. Don't forget that they left behind a negative. So now I'm getting really close. I have the limit as x goes to 0 of negative 1 times 1 is 1 over 4 times x plus 4. Notice I don't have a plain x in my denominator. I have x plus 4. So it's totally legal to use 0 in place of x because I will not be making a 0 in my denominator. So now I know it's time. I can leave the limit notation off. This is 1 over 4 times 0 plus 4, which is 1 over 8. Final answer. So that's 3 algebra techniques you could use if you have a limit of a function that is not well defined, or a limit of a function that is not well defined, that is not well behaved at the x value you're interested in. You could try factoring and canceling. You could try rationalizing the numerator, and you can try getting a common denominator, which is another way of getting your denominator, which might be a variable, getting your denominator to cancel out. There you go, guys.